Okay, let's dive into this. Welcome to today's Explainer, where we're taking a really close look at Grade 7 robotics. Specifically, we're on a mission to troubleshoot a classic, and I mean classic, problem. We've literally all been there. You build this awesome robot, you hit start, and it just spins in a circle. Or maybe it just confidently drives right off the table. So, today is a misconception check all about program flow, and we're going to map out exactly how you can take total control of your machines.
Right off the bat, I want to pose our essential question for today. How can precise instructions make a robot move reliably? I really want you to think about that for a second, because this question right here, it's the core mystery of robot movement. Like, why doesn't the robot just do what we want it to do? We put the motors in the right place, we connected the brain, everything is plugged in. So, what gives?
Well, that brings us to Section 1, the robot control mystery. Seriously, have you ever caught yourself throwing your hands up in frustration and yelling, "The robot should just know what I mean"? It is incredibly common in 7th grade robotics, but it actually highlights a massive knowledge gap about how robots actually process information. We naturally expect them to understand our intent, but the harsh reality is they simply don't. They don't have a human brain that just magically fills in the blanks for them. Think about how we process the world. If I tell you to go out the door, your brain automatically infers the missing steps. You know you need to stand up, walk forward, reach out, grab the handle, pull the door open, and then walk through. You assume all of that context based on your entire life experience. A robot, on the other hand, it requires explicit, hyper-precise commands for absolutely every single micro-action. They have zero human intuition. If you don't explicitly tell the robot to power on the motors at a specific speed for a specific duration, well, it's just going to sit there staring blankly at you. Now, what's really interesting about this next part is how we actually solve that problem. Section 2, giving precise instructions. Before we can even think about writing complex code, we have to lay down the foundations for reliable movement. First things first, we always start with safety rules. You know the drill. Wear your safety goggles, keep loose clothing away from those spinning gears. Then we need to understand the motor basics. Once we have that down, we write our initial basic movement commands and physically test that motor behavior. And hey, quick pro tip here. Test your motor behavior while holding the robot safely off the desk. That way, it doesn't immediately drive off the edge and shatter. This whole setup and testing phase is absolutely required before any of the heavy-duty programming actually begins.
So, once we know the basic hardware works safely, we graduate to our essential question from Unit 3. How does program control flow make robot behavior more flexible? This right here is our bridge. We're moving from just testing basic motors to actual structured programming, because ultimately, we want our robots to do way more than just drive in a single straight line forever, right? We want them to navigate complex mazes, complete difficult tasks, and make dynamic choices on the fly. Which leads us perfectly into Section 3, fixing program flow misconceptions. First, let's clearly define our terms so we're all on the same page. Program flow is the structured order in which a robot executes commands, preventing unpredictable behavior. Think of it like a roadmap you're handing directly to the robot's brain. Without a crystal clear, turn-by-turn map, it's going to get completely lost, or worse, just confidently crash itself right into a wall. To build that roadmap, we use core program flow tools. We have sequencing, which is the exact order of your steps. We have loops, which repeat steps for us so we don't have to. We have conditionals, which are basically if-then decision-making steps, like if you see a wall, then stop. And finally, we have functions, which are like little mini-programs bundled up inside your main program to handle very specific tasks. These 4 elements are our absolute go-to tools for taking an unpredictable, erratic robot and making it behave exactly as we planned. Let's look a bit closer at that first one, because sequencing is everything. Commands must be in the exact right order. Imagine you want your robot to drive forward toward a wall and then turn right to avoid it. If your sequence is mixed up and you accidentally put the turn command before the move command, well, the robot might just pivot in place and then confidently drive itself straight into the brick wall. It did exactly what you wrote. It just wasn't what you meant.
Now let's see how this builds with our next tool, loops. Just think about the contrast between these two scenarios. Without loops, if you want a robot to take 10 separate steps forward, you're sitting there writing the exact same move forward command 10 individual times. It's completely exhausting. But with loops, you write one single command and just tell the robot to repeat it 10 times. Done. Program flow tools like this organize our code beautifully and save us from incredibly tedious repetition.
All right, moving on to the final piece of the puzzle. Section 4, testing and debugging behaviors. Because let's face it,
inevitably, things are going to go wrong. And that brings us to debugging, defined as the process of finding and fixing errors in your robot programs. So, the crucial point is this. Making mistakes isn't a failure in robotics. It is quite literally a core part of the process. You are completely expected to find bugs. In fact, if you're finding bugs, it means you're doing it right. You're pushing the limits and you're learning exactly how the system reacts.
To fix those bugs when they pop up, we follow this exact step-by-step troubleshooting guide. Step 1, run your basic movement command. Step 2, stare at that robot and physically observe what its motors actually do in the real world. Step 3, revise your code based entirely on those real-world results. You watch, you learn, you adjust. It's just a continuous loop of improvement.
Let's walk through a real-world example to see this in action. Say your expectation is that the robot moves forward, but in reality, the motors spin in opposite directions, making the whole thing spin in a frustrating circle. So what's the fix? You need to check your sequencing and revise those basic movement commands. Maybe one motor is physically wired in reverse, or maybe your code is sending a negative power value to the left wheel by mistake. Now, what if you expect the robot to turn just once? But the reality is it spins endlessly. Then you need to debug your loop or conditional program flow. Maybe you just forgot to tell the loop when to stop. The big takeaway here is that observing the physical test results directly dictates exactly how we revise the code.
We've covered a ton today, how to make precise instructions and how to fix our own program flow errors. But I want to leave you with this provocative question as we look ahead to our sensing unit. What happens when your precise program suddenly has to react to an unpredictable environment? Because let's be real, the real world isn't just an empty, flat table. It's messy. Next time, we'll dive into how environmental detection and input data become our next big mystery to solve. Thanks for joining me for this explainer, and keep testing those commands.